So, welcome my friends, welcome to my next lecture. So, now this lecture I will talk about more on vector fields. Okay. In fact, if you remember in my last class I talked about kind of definitions of vector field. Okay. And of course, my plan is to talk about what is called gradient, divergence, curl and Laplacian in couple of lectures, coming couple of lectures. So, but for that I need the concept of what is called vector field. So, I have defined the notions of vector field and then I give couple of examples. Then there are ways of visualization. Then you can visualize your vector field. And then there is a what is called integral curve. One of the way you can visualize is the by arrows that I have explained via a kind of some pictorials or via examples. So, now integral curve also in that way also you can visualize your what is called vector field. So, I think I will start from that, that means how to calculate an integral curve given a vector field. And then I will talk about what is called divergence and curl and Laplacians if time permits, or maybe in the next lecture or coming 1 or 2 lectures. Okay. So, as I said, so in my last lecture also I have discussed what is integral curve given a vector field. If I have a vector field, what is integral curve? Okay. So, and as I said, I think you can calculate like if I give some vector field, you can calculate at least of course in specific dimension like R2 and R3. So, before that let me just recall what is integral curves. Okay. So, this is the definitions I already explained in my last lecture, again just recall it. So, let capital F be a vector field. Suppose you have a vector field over domain D, an oriented smooth curve C, okay, an oriented smooth curve C in domain D, and suppose that oriented smooth curve C has a parameterization RT, that is exactly I have written. So, an oriented smooth curve C with parameterizations R of t in my domain D, it is called an integral curve of F if the following conditions satisfied. What are the conditions? If I take every point P in C, so that suppose if I am in R2, so this is my C. So, if I take any point P in C, first condition is that the F of P, that means F is a vector field, right? It is a map from your domain D subset of R2 to R2 because I define 2 dimension, or D subset of Rn to Rn. So, first observation is that capital F acting on P should be non-zero, number 1. And number 2, I have to assign a vector at the point P, that means the F acting on P, that means that is nothing but the vector I am assigning a point P. And what is that vector? It says that Fp has the same direction as the unit tangent vector Tp to C at the point. So, that means this is the tangent vector at the point C. Okay. So, this is P, right. So, what is Tp? Tp is the tangent. So, I think if I write, so for example, if this is my point P, so what is tangent? So, this is my tangent. So, this is my point P, this is Tp. Okay. Or in terms of parameterization you can write what is my P? P is a point in the curve. So, it is like R of t, some t, and what is Tp? This is nothing but R prime of t. Okay. So, that means a curve, if I have a vector field on some domain D, a smooth oriented curve C with parameterizations R of t in the domain D, I will call that it is an integral curve of my vector field capital F. If I take any point P in my curve C, or maybe if I take some point R of t which is same as some point P in C, means what? It should be exactly equal to P is exactly equal to R of t for some t in the closed interval A B, because R is the parameterizations. For that point F of P should be non-zero, number 1, and what is the corresponding vector at that point? So, that means what is capital F of P has the same directions as the unit tangent vector Tp, which is nothing but R prime of t to C, okay, at the point P. So, that is exactly I have written F of RT is nothing but exactly equal to R prime of t. If these things happen, then I will say that the corresponding curve C is an integral curve. So, obviously, since I am talking about the tangent, so therefore, capital F is a tangent or velocity or like vector field, tangent vector field or velocity vector field on the integral curve, and thus integral curves provide a geometric pictures of a vector field, because I can each point in the curve I have a what is called corresponding vector, and which is nothing but the tangent vector. As an application, so like if I have a force field, the integral curves are called the lines of force, and in a fluid field integral curves of the velocity field are called the streamlines or flow lines. But as I said, given a vector field, you can calculate, like if I mean say 2-dimensional vector field or 3-dimensional vector field, you can calculate. And how to do that? You have to solve partial differential equations. So let me see, yes. So that's what. So finding integral curve of a vector field. What is that? So start with the vector field. Again, I am talking about a vector field capital F from some domain D subset of R2 to R2. Okay. So that's kind of vector field. I am in a specific domain. Okay. So start with a vector field capital F, it is some domain D subset of R2 to R2, whose first component is F M, capital M of xy, second component is capital N of xy. And if I have vector field capital F is like that, the integral curve at the point x comma y, okay, the integral curve at the point x comma y is the solutions of these differential equations. Okay. So you have to solve this differential equation, dy by dx is exactly equal to capital N xy divided by m xy at the point x. So if I solve these differential equations, then the curve I will get, which is nothing but the integral curve at the point x comma y. Okay. This is in 2 dimension. Similarly, in 3 dimension, how you proceed? If I have a vector field whose component are capital M, capital N and capital P, then the integral curve may be viewed as the solution of the ordinary differential equations. So x prime of t, of course, that means that I am talking about the parameterizations of the curve. So x prime of t is equal to m, y prime of t is equal to capital N and z prime of t is equal to capital P. So if I have this differential equation x prime, y prime and z prime, if I solve these differential equations, it will give you a integral curve along the point x, y, z. Okay. So this is for 2 dimension, that means if it is of the form m I cap plus n j cap, then dy by dx is equal to capital N by capital M, and you have to solve this differential equation. Then the solutions at the point capital X, which is x comma y, it will give you the integral curve. I think if I calculate one example, it will be more clear. Let me see. Yes. So this is the examples. I have given a very particular examples how to calculate integral curves. So examples of vector fields and their integral curves. Okay. So what is the vector field? So this vector field I think you are familiar with. In my last lecture I said, so this is a vector field. So f of xy whose first component is minus y and second component is x. That means it is a rotational vector field, if you remember, and rotation with the angle anticlockwise directions with the angle pi by 2. So that's vector field we know. In fact, this is the corresponding what is called arrows identifications. If I have the arrows identification, this is the identifications. So that means what is the map? xy goes to minus y comma x. So this is the vector functions from R2 to R2, and this is the corresponding vector field, and at each point I am assigning a vector. That means you start with a vector xy anticlockwise direction, you can go up to pi by 2 angle with angle pi by 2, and that is the vector I am attaching with at the point xy, and that will give you a what is called rotational vector field. This is the arrows identifications I already discussed. This is the one. Now I am saying that what is the corresponding integral curve for this vector field. Look, so just now I said if it is of the form mxy plus I times nxy. So what is my mxy here in that case? Mxy is nothing but minus y, and what is my nxy? Nxy is nothing but x compared to the earlier slides. So this is m, this is n. Okay. So that means what I have to do? So if I take any point pxy with second component is non-zero, because I need that p of xy should be non-zero, right, if you remember. Okay. Then I have to solve the differential equations. That means the dy by dx is exactly equal to minus x by y. Now this is a very simple differential equations, right? If I solve it, what solution I will get is this one: x square plus y square is equal to a square. So that means it will give a circle. Okay. So therefore these circles x square plus y square is equal to a squares are the integral curves of my vector field capital F. Now look, you see, you can also guess actually. For example, the ways arrows are given, that means the corresponding the way direction is given. So I mean this will give you one circle, this is give you another circle, okay, and so on and so forth, and exactly this is the corresponding identification. So that means the directions if I put it, that means this is the direction, this is one direction, right? So this is the corresponding what is called integral curve. Therefore, if I have an integral curve, then also I can visualize my corresponding vector field. Now this vector field I can visualize in terms of arrows, and this is in terms of what is called integral curve, and you have to solve in this way. So that means you have to just solve the corresponding differential equations. Okay. So this is one. Another example I have studied, what is that? This is like flip kind of thing. That means xy goes to yx, right? So x comma y goes to y comma x. That is the vector functions R2 to R2. So this is I think right, x comma y to y comma x. Okay. So now Again, I think I have discussed this vector field, and in terms of arrows, what is the visualization? This is the visualization, right? So at each point, so this is the corresponding visualization for this vector field, x y goes to y comma x. Okay. So now I have written this is capital J. Now what is the corresponding integral curve for these vector fields? Again, since what is my, if I just compare with the m x y times I cap plus n x y times j cap, what is my m x y? So m x y in this setting is y, and what is my n x y in this setting is x. Then if I take a point p x y with y is non-zero, then I have to solve this differential equation n x y divided by m x y. That means capital N divided by capital M, that means x by y. Now it's a simple differential equation, right? Now if I solve it, what is the solution? Y square minus x square is equal to a. That means it will give you the hyperbola. Okay. So therefore these hyperbolas y square minus x square is equal to a are the integral curves of G. In fact, you can also guess the way its arrows is giving, it's like this, it's like that. Okay, it's this. So it is okay. So that means again this. So that means a priori from the arrows you can get it should be like that, and answer is yes if you calculate the integral curve. So this is the integral curve. See? Okay. So this is kind of directions. Okay. So therefore in terms of integral curves also you can visualize what is called your vector field. So I have two simple examples I have discussed. So many examples we will have, and you can calculate the corresponding integral curve. Okay, so now there is another concept what is called path independence field. So that means if I have a vector field, so there is a notion called path independence. Now from the word path independence, it's kind of quite clear. I am talking about that something which should be path independent. That means whatever path I will take, that whatever the concept or whatever the object, that will be invariant under path. So that's kind of things you can have it in your mind, and in fact in particular what is that? Look at the definitions. It says that okay, start with a vector field capital F with domain D subset of Rn to Rn, and it is a continuous vector field. That means C1 vector field I am talking about. Suppose let capital F be a C1 vector field. We say that the vector field capital F has independence of path on my domain D. Okay. So suppose you have a vector field, second I am starting with R2 to R2. Okay. So suppose this is my domain D and this is the corresponding vector field. Okay. Or you can have, suppose you can write it at each point D you have a kind of vector, some arrows. So that's also you can, so the in terms of arrows you have that one. Okay. What it says is that if I have a vector field and suppose it is a nice vector field, that means a C1 vector field, that means continuously differentiable vector field, continuous vector field, that means it is very nice vector field. I will say that if every pair of piecewise smooth oriented curves C1 and C2 in the domain D, so that means I am taking two curves, one is C1, another is C2, both of them are piecewise smooth oriented curves. So for example, I am taking this kind of curve. So one curve is this one, say let it be C1, and another curve is this one, let it be C2. Okay, but there is a catch. What is the catch? C1, C2 in the with a common initial point and common final point. So that means this will not work. So I mean this C1, C2 will not work. But I have to be careful here actually. Okay, so what is that? So maybe I should erase it. Okay. So what is that? Suppose this is my domain. Okay, and suppose at each point you have a vector associate. So this is nothing but a vector field. Now suppose take a point here, take a point here. Now you can consider two curves. So this is my C1. And suppose this is my C2. Two piecewise smooth oriented curve, but initial point and final point should be same. So this is my initial point and this is my final point. And suppose this is my orientation C1, C2. So if I have a point, 2 point, or if I take two piecewise smooth oriented curves in my domain D with the same initial point and same final point, then what it says is that the integral of capital F, that means the, I should say the path integral of my vector field capital F on C1, which is same as the corresponding path integral of capital F over C2. So that means of course in my next lectures, not next lecture, maybe after 1 or 2, 3 lectures, I will start with what is called line integral or vector line integral. I will introduce those kind of integral, and then it will be more clear what is the meaning of that one. But I think in the beginning of my lectures, I think I have discussed if I have a nicely oriented path with the parameterization say r of t, then what is the meaning of this path integral? So, if you remember that path integral meaning is that suppose I have a contour, you can say the contour. So, that C is very nice, say with the parameterizations r of t, then what is the meaning of this path integral capital F dr? If you remember, suppose this is my parameterization and say t running from a to b, then what is this? This is nothing but integration from a to b capital F of r of t, okay, then you have r prime t dt. So, that is the integration you will see. Okay. So, that is the meaning of this symbol. So, this is a symbol integration over C capital F dr, which is nothing but the contour integral or path integral of my vector field capital F. So, that is the notations, and what is the definition? Definition is that if my what is called that curve C has a parameterizations r of t, then this exactly by definitions a to b, because this t running from a to b, capital F of r t times r prime t dt. So, that integral you have to calculate. Anyway, so in my after 1 or 2 lectures when I will talk about more on integrals like line integral, vector line integral. So, that time I'll just repeat once again. If you remember, I think in my beginning of my lectures I have defined something like that. Okay. So, it says that if I have a vector field, okay, which is nice, and in the domain if I take two nice curves, that means two piecewise smooth oriented curves, with the fact that the starting point and common initial point and common final point. So, that means common initial point, common final point. If this is the case, then what I want is that we have that integration over C1 f dr, which is exactly equal to integration over C2 f dr. So, that means it is independent. That means whatever path I can take with that same initial point and same final point, the integration will be remain unchanged. It does not matter which path I am actually doing the integrations. Okay. So, that is why. So, every pair of piecewise smooth oriented curves C1 and C2 in D with common initial point and common final point, we have that the integration over C1 path integral or contour integral over C1 of capital F is same as path integral or contour integral of C2 capital F. This will be same. Okay. Anyhow, when I will talk about one example, I will calculate after 2-3 slides, then it will be clear. So, one example I have written. So, for example, if you consider this vector field f of x y is equal to 4 I cap plus 7 j cap, it has independence of path in R2. Of course, here it is defined in full R2. So, that means what? In R2, if I take 2 points, if you take any curve say C1 and say C2, then if you calculate this integral, integration C1, this capital F dr, which is, if you calculate it, that value is exactly same as integration C2 capital F dr. But provided the C1 C2 will have, so suppose this is the same initial point and this is the same initial, suppose this is P and this is Q, okay. But once I have a curve C1 which the initial point is P and final point is Q, and take another curve C2, initial point is P and a final point is Q, but you need to know the parameterization, right? Then only you can have the what is called, by definition you can calculate this integral as well as this integral, and you will see the both values should be same. So, therefore, it is actually independence of path. Okay. So, that is why this definition path independence. Okay. So, that means if I have a nice vector field with my domain D, we say that that vector field as independence of path. That means if I take any two piecewise smooth oriented curve with the same initial point and the same final point, any to any pair, okay, the integration over C1 capital F dr is exactly same as integration over C2 capital F dr. So, that is the meaning of what is called path independence. Okay. Same thing, or I should not say same, you can see that actually this is same. Okay. So, because what will happen, so this is what, so look here, so suppose this is my direction. Okay. So, this is C1, this is C2, and that is same as C. If I start from here, if I go this pair, this point, and then I will come back. So, that means you can have C1 union minus of C2, and that means this is actually a closed contour. Means I am starting with point here, then I am moving in this direction, and then I am come back here. So, that means it is a closed curve. So, that means in terms of closed curve, you can say that the integration should be 0. Okay. Anyway, so later on you will see, but this is sometimes called what is called conservative field. What is conservative field? This is my definitions. Let capital F is a vector field with domain D subset of Rn to Rn, and which is nice. I will say that the vector field capital F is said to be a conservative field on D if the vector line integral, this is actually 0 again, as I said. So, I will talk about this vector line integral after 2-3 lectures, then you will see exact the definitions and more examples, then it will be more clear. But anyway, I already said that this integral you can interpret as if C has the parameterizations R of t, say from t running from some interval a to b. So, this integral is nothing but a to b. So, this integral is nothing but a to b f of r t then r prime of t dt. Okay. So, I will say that a vector field is a conservative vector field in the domain if I take any what is called, you see, every piecewise smooth oriented closed curve C in D. So, that means suppose if I am in R2, suppose this is my vector field. So, suppose vector associated at each point. If I take any piecewise smooth, say suppose this is my C. Okay. So, every piecewise smooth oriented closed curve C in D, or you can have it something like that. This is also piecewise smooth, right? This is also C. So, it says that okay, start with a vector field with domain D. I will say that that vector field is conservative field or conservative vector field if I or take any piecewise smooth oriented closed curve in D, then the vector line integral of capital F over this contour C is 0. That is what it is. And later on you will see that is same as my vector line integral is independent of path. That means, if I take any 2 points, whatever path I can take with the initial point say P1 and final point is P2, same initial point and same final point. Whatever path I can take with the same initial point P1 and same initial point P2, the vector line integral over that path will be same. And that is same as if I take any piecewise smooth closed contour in my domain, the vector line integral of capital F over this contour, simple piecewise smooth simple closed contour, the integral is 0. So, that exactly. So, therefore, I am saying that it is a vector field, it is nice. I will say that this vector field is conservative field if the vector line integral C of f dr is 0, and what is my C? This C is nothing but piecewise smooth oriented closed curve C in D. Again, the same example I am saying that okay, consider this vector field and this is a conservative vector field in R2. So, you just take any closed contour, any piecewise smooth oriented closed curve, whatever you can take, and once I have that, and suppose you have a parameterization R of t, you just perform this integral, you will see the integral will be 0. But later on you will see that conservative vector field and the earlier vector field, that means this is the one path independence, both are equivalent. So, as I said, path independence field and conservative field both are equivalent. I will talk about after 1 slides. Okay, let me just do one example. Okay, so this example says that there are examples of what is called non-conservative vector field. So, this is the example says that okay, you have a vector field, look, this is my vector field, but here actually it is not a conservative vector field. That means, I will have a simple piecewise smooth closed curve, but the integral is not vanishing. Okay. So, what is the meaning of conservative field? That means, every piecewise smooth oriented closed curve C I can take in my domain D, the integral has to be 0. But this here is the example where you have the vector field, but if I take a piecewise smooth simple closed curve in my domain, but the integration over the vector line integral of capital F over this C is non-vanishing. Let us see. So, suppose this is my vector field capital F x y, which is minus y I cap plus x times j cap divided by square root of x square plus y square. That means, what is my capital M in this setting? Here my capital M, which is nothing but minus y divided by x square plus y square, and what is my capital N, which is nothing but x divided by x square plus y square. Okay. But you have to be careful here, this here is my domain not in R2, but I am actually taking R2 and taking out the origin. That means, I have a punctured what is called plane. Okay. It is not a full plane, it is a plane, but I am taking out the origin, that means a punctured plane, and you will see later on that domain plays a role actually whether my vector field is conservative or not. So, here actually domain it's not good domain because it's punctured. Okay. There is a hole in my domain. So, and then you will see if I calculate the corresponding vector line integral, it will actually give you some non-zero number. Okay. So, now I am taking a very simple closed piecewise smooth closed curve. What is that? C is equal to RT. That means, I am talking about the circle. Look at the parameterization, the cosine t sin t, t running from 0 to 2 pi. That means, it is actually a circle of unit radius. Okay. This is cycle. And this is the origin. So, that means, I have a circle with parameterizations R of t with unit radius, and this is my origin. Now, you calculate this vector line integral, that means integration C f dr, and as I said, once I know my parameterization of C, then I know the definition, right? What is that? So that means t running from 0 to 2 pi, so that means 0 to 2 pi, capital F of r t, r prime t dt. You know capital F, you know r prime, then you can calculate it. What is capital F of r t? Of course, capital F of r of t. R of t means this is cosine t comma sine t. You put it there, so therefore it will come up, I think, minus sine t comma cosine t. F of r t will come, then you have r prime t, that means the corresponding dot product, because this is a vector, right? F of r of t, F capital F bracket r of t is a vector in R2. Similarly, r prime of t, it is a tangent vector, right, on that curve. So, it is also a vector in R2. So, F of r t times r prime of t, it is nothing but the dot product or inner product. So, that exactly I have written. So, that means this is the dot product. So, okay, if I have r t like that, what is r prime t? The component wise derivative, that means minus sine t comma cosine t, that means r prime t, that is the corresponding vector attached with the point r of t. Okay, and what is capital F of r t? In capital F, you know what is my capital F functions, capital F of x y, which is nothing but minus y divided by x square plus y square, comma x divided by x square plus y square. Okay, you just replace x comma y, this point by r of t, and you will end up with what is called minus sine t by cosine t. Because what is r of t? Cosine t sine t. So, that means if you just replace, so if we write f of r of t, which is nothing but f of cosine t comma sine t, and this is the corresponding formula, right? If I have it, so denominator cos square t plus sine square t, so it will be 1. So, that means what we will have minus sine t comma cosine t, and that is exactly the case, right? This is the one, and this is the derivative. So, take the inner product. So, you will have sine square t plus cosine square t times dt, it is 1. So, it will end up with 2 pi, and which is a non-zero number. So, therefore, this is a vector field which is non-conservative. Okay. And as I said, so because this vector field is a vector field on a kind of bad domain, I should say, because domain is punctured plane, which is not so nice, and that is why this phenomenon is going on. And later on I will talk about that. If your domain is not that good, so this kind of examples you will have. So, I am saying that okay, capital F is not a conservative field in this term, that is very important. Okay. So, domain is very important. Okay. So, now I think it is clear. So, path independence, and you have two kind of varieties of vector field I am talking about. One is the path independence, another is the conservative vector field. Path independence means what? If I start with a nice vector field, if I take a domain D, and if I take any pair of what is called piecewise smooth oriented curve C with the same C1, C2 with same initial point and same final point, then the corresponding vector line integral over C1 of capital F is same as vector line integral of capital F over C2. So, that is same as, that is the what is called path independence. And what is called conservative? Again, start with a very nice vector field. I will say that that vector field is conservative if I take any piecewise smooth oriented closed curve inside my domain D, then the corresponding vector line integral of capital F over C is actually 0, and later on you will see both are equivalent. Okay. Path independence and conservativeness for nice vector field. Okay. So, before that, let me talk about what is called scalar fields. Okay. So, what is scalar fields? So, from the term it is clear that scalar field means, that means I am talking about a kind of field which is taking values real number, and answer is yes. So, look, a functions f with domain U subset of Rn to R is called a scalar field on U as it assigns a number to each point of U. So, that means I have a functions from the domain U subset of Rn. Okay. Now, I am assigning at each point of U with a scalar. Okay. So, earlier vector field means what? If I have a functions capital F from subset D subset of Rn to Rn, that means I will say that is a vector field. At each point of my domain D, I am associating a vector, right? That is why I am saying this is a vector field. Now, scalar field means what? Again, I am having a functions f from some domain D or U subset of Rn to R. This time I am associating each point U in Rn scalar, that is called scalar field. Okay. So, for example, the temperature of a metal rod that is heated at one end and cooled on another is described by a scalar field capital T x comma y comma z. The flow of heat is described by a vector field. Okay. The temperature is described by a scalar field, whereas the flow of heat is described by a vector field, and the energy or heat flux of my vector field is given by, okay, what is this? This is gradient of T. Okay, you have a scalar field T, then what is the gradient? It's a vector valued function, right, with vector variable. So, if I have a scalar field F from U subset of Rn to R, and what is the gradient of T. So, okay, not Ft. If I start with a scalar field capital T, which is a map from Rn to R, then if I take the gradient of T, then it will be a map from U subset of Rn to Rn. So, that means if I take the gradient of my scalar field, it will be a vector field, and that is exactly the case. The energy or heat flux vector field is given by J, which is nothing but gradient of T times minus of kappa, where kappa is positive, some constant. So, that is the thing. Okay. And one definitions I am adding here. So, if I start with a vector field capital F in Rn, since it is a vector field in Rn, that means it is a functions from some domain subset of Rn to Rn, that means it will have n components. So, I am writing capital F as F1, F2, Fn for, and what is F1, F2, Fn? It is a map from D subset of Rn to R, that means each of them is a scalar field, right. Okay. So, for some scalar fields F1, F2, F1, F2, Fn in Rn, small f1, small f2, small fn in Rn, I will say that capital F, that means my vector field is Ck vector field, that means k times continuously differentiable vector fields if the corresponding scalar fields F1, F2, Fn, these are Ck functions, that means these functions are k times continuously differentiables. Okay. So, that means now I will say that if capital F is Ck vector field, that means since it is a vector field, it will be a map from some domain subset of Rn to Rn. It will have n components, and what are the components? Small f1, small f2 up to small fn. Each f1, f2, fn, it is a map from domain subset of Rn to R, that means each of them is a scalar field. Okay. And I say that capital F, my vector field is Ck, that means k times continuously differentiable vector field if and only if my corresponding scalar fields F1, F2, Fn, small f1, small f2, small fn, these are actually k times continuously differentiable. And there is a note I have written, all vectors field are assumed to be C1 unless otherwise noted. That means in my next slides onwards, whenever I will talk about some vector fields, by default I am assuming it is a C1 vector fields, that means continuously differentiable vector field. You will see many things. It will be very nice if I deal with what is called C1 vector field. Okay. So, now I talk about, since I talked about scalar field, vector field I have discussed, then I talked about scalar field. Now, since I have a scalar field, what gradient you know, like if I have functions f from Rn to R, then what is the gradient I already discussed when I talked about what is called partial derivative, direction derivative, right. In fact, after the definition of partial derivative, I think I talked about what is called gradient of f. So, now I have a scalar field, that means I have a function some domain subset of Rn to R, and suppose it is nice that scalar field, and then I can talk about the gradient, and gradient is a vector field, you see. So, okay. So, I am denoting, so del, so this symbol, it is called the del operator, which is given by del, which is, that means del del x1, del del x2 up to del del xn. That means I have a scalar field from some domain Rn to R, right. So, that means how many variables x1, x2, xn, n independent variables. So, I am defining the corresponding del operator, del del x1, del del x2 up to del del xn. Let f be a scalar field on my domain D, then I am defining that gradient of f, which I denote as grad of f, and is defined by, I think I have already defined when I talked about partial derivatives. So, grad of f, which is nothing but del f del x1, del f del x2, del f del xn, whenever it exists. So, that means if I start with f is a small f, or the scalar field is a C1 scalar field, then of course gradient of f is exist. Okay. So, that is what. So, therefore, what is, so once again, so if I start with a scalar field, nice scalar field, say C1 scalar field, then gradient of f, it is a vector valued functions with vector variable, whereas I am starting with a scalar field, that means I have a scalar valued function with vector variable. If I take the gradient of f, it becomes a vector valued functions with vector variable. That means if I have a scalar field, if I take the gradient, it will be a vector field. So, look at the note here, the gradient of a C1 scalar field is a vector quantity. Of course, it is quite clear from these definitions, grad of f. Okay. So, therefore, grad of f, it is a map from some domain, or maybe let it be very nice, some domain subset of Rn to Rn. And what is that? Grad of f at, say, so if I write say a1, a2 up to an, and what is that? This is del f del x1 at the point a1, a2, an, then del f del x2 at the point a1, a2, an, up to del f del xn at the point a1, a2, an. Okay. So, that means if I have a scalar field, if I take the gradient, it will be a vector field. That is exactly I have written. Gradient of C1 scalar field f is a vector quantity, and therefore, for a C1 scalar field f, if I take the gradient of f denoted by capital F, it forms a vector field. Okay. And this kind of vector field has a special name, that is called gradient vector field, because I have a scalar field, I am taking the gradient. then a special type of vector field. So, this kind of vector field later on you will see I will call this is as a what is called gradient vector field. Okay. That means gradient of a scalar field is nothing but the gradient vector field, and this is a very special type of vector field. Okay. So, couple of properties of gradient of a scalar field. Okay. So, let f and g, suppose I am starting with two scalar fields, and suppose you have two real constants, then if I take the gradient of a plus bg, so a will come out, b will come out, this is gradient of a plus b times gradient of g. That means the del operator is a linear operator, this is the linearity. Okay. And this kind of Leibniz rule, if I take the gradient of f times g, which is f times gradient of g plus g times gradient of f. Similarly, if I take the cosines, again it is the Leibniz rule. So, it says that gradient of f by g, which is g times gradient of f minus f times gradient of g divided by g square, provided g is non-zero. And this is sometimes called actually what is called chain rule or composition. It's like if h is a function from domain D subset of R to R, and suppose the range of the scalar field f lies in the domain, otherwise h composed with f does not make any sense, right. H composed if f does not make any sense if I say that range of f should be in the domain of h, otherwise it does not make any sense. Second, h composed f is a map from Rn to R. Okay. So, that means the range of f should be the domain of h. Okay. That is exactly I have written. So, if h is a map from D subset of R to R and the range of the scalar field f lies in the domain of domain D of h, then h composed f makes sense, and if I take the del operator on that or gradient, which is nothing but the derivative of my h at the point g times gradient of g. Okay. So, of course, this is a scalar multiplication because h prime of g is a scalar, because h is a map from R to R, okay, times gradient of g. Okay. So, I think I just defined what is called gradient vector field, I already said, and maybe in my next lecture I will start with some examples of this. So, what is gradient vector field? So, it says that suppose you have a vector field capital F, okay, that means it is a map from some domain D subset of Rn to Rn. I will say that that vector field capital F is a gradient field or gradient vector field on my domain D if there exists a scalar field f, you see, such that your capital F, you can get back your capital F, which is nothing but the gradient of f. So, that means a field, suppose I have a vector field capital F, I will say that this is a gradient field or gradient vector field if there exists a scalar field small f, such that if I take the gradient of f, it will be a vector field, and that should exactly coincide with my vector field I have started with. So, therefore, let capital F be a vector field. The vector field capital F is said to be a gradient field if there exists a scalar field such that capital F of x, which is nothing but gradient of small f at x. So, that means I have this capital F vector field which is nothing but gradient of f, and in such a case I will say that the corresponding scalar field is called the scalar potential of my vector field capital F. Okay, one very easy example I have given. So, the vector field, if I consider this, that means x y goes to y comma x, if I have this vector field, this is a gradient vector field. That means I will have a scalar field, and if I take the gradient of f, which is exactly coincide with my vector field capital F. And what is my functions? So, this is capital F is equal to gradient of small f, and what is my small f? Small f is nothing but x times y. Okay, you just take the derivative, you will do that. Maybe next class I will do that. Okay. So, therefore, this capital F is nothing but grad of small f, and small f is a scalar field. Okay. So, that means capital F is a gradient vector field, and there is one result, I did not prove it actually. Suppose you have a vector field capital F, and suppose it is a gradient vector field. Now, point is that if I take two scalar field and if I take the gradient, if I get the same vector field, they say that these two scalar potential or scalar field, they actually differ by a constant. In other words, any two scalar potential of the same vector field. So, that means suppose capital F is equal to grad f1 same as grad f2. Then it says that this is scalar potential. So, f1 and f2 are scalar potential. You have two different scalar potential, but one side taking the gradient of that, it will give you the same vector field or same gradient field, right, f. Then say that f1 and f2 differ by a constant. You can have it, that result. I think I should stop here. Next class I will start with one example. So, this is of course one simple, very simple example. There are many examples you will see, and those vector field actually nice, like. So, that means you can have the vector field in terms of scalar field. That means you have a scalar field, take the gradient and the corresponding vector field I am saying that it is a gradient vector field. Okay. So, then you will see once I have a gradient vector field, then the corresponding, like I have defined the given vector field, I have defined like what is called path independence, and then what is called conservative. So, now if I talk about gradient vector field, the special kind of vector field, you will see kind of some connections with that path independence and the conservative vector field. Okay. So, I think I will talk about in my next lecture. I think I should stop here. Thank you.